Hello, hello. Here we are again with Halil Ibrahim Kalkan. He is the founder of Volosoft, and today he will talk to you about designing modular monolith for microservice architecture. And without further ado, we are with you.
Thank you, Bige. Hello, everybody. I am Halil Ibrahim Kalkan. I am one of the co-founders of Volosoft, and also I am the lead architecture and developer of the ABP framework from the first day. So probably most of the people already knows me. Today, I will talk about creating a monolith first application that's easy to convert to microservice system later. So how to design it to make it microservice compatible or easy to migrate later. And also I will mention about the migration steps. Okay, let's start from the agenda first. I will start with defining what is the microservice and also what's the monolith first approach. And then I will mention about how to design a modular monolith system by using layering, by designing the database, and finally integrating the modules with each other. Then in the second part, I will talk how to migrate this system to a microservice system by changing the hosting system and changing some configuration to align with distributed systems. Replacing in-process service calls with REST API calls, and enabling database transactions with transactional events, and handling database migrations and changing authentication and authorization settings on the system. Finally, I will mention about deployment a bit. Let's start from the beginning. Okay, everybody, I think everyone knows what is a microservice. So I will start by introducing the benefits and costs of a microservice system development. Why we are developing microservice systems? Because it forces modularity and encapsulation. So even if we, actually there is no chance to, by mistake, to break this modularity and encapsulation, because it separates modules into different services. So they communicate over well-defined rules. So to implement modularity, it's a good approach. A microservice can be independently developed, deployed, and also scaled independently from the others. This is another benefit. And also technology diversity. That means you can use different database technology, for example, in one microservice, or you can create a microservice in Java. Another one is .NET. So you can use different technologies for each component because they are completely independent systems, subsystems. But there are some also costs. Otherwise, we all use microservice architecture. The main cost is distribution. Because of distribution, it's hard to develop such a system. Instead of immediate consistency, now we should deal with eventual consistency, and also deploying, monitoring, logging, and managing all this distributed system is complex. So you need a DevOps team and so on. So who is for like microservice systems? Who should develop a microservice system? If you have a large development team with a DevOps and automation culture, and you have a major business or domain which is large and complex, then your project is candidate to be a microservice. It shouldn't be, but it can be. Who is not for? Actually, Martin Fowler is one of the advocates of microservice systems. He says that my primary guideline would be don't even consider microservice unless you have a system that's too complex to manage as a monolith. The majority of software systems should be built as a single monolith application. Do pay attention to good modularity within that monolith, but don't try to separate it into separate services. So Martin Fowler says that it's good to start monolith first. And he says you shouldn't start a new project with microservices, even if you are sure your application will be big enough to make it worthwhile. That means even if you will create a microservice system and you are sure about that it will go like that, you shouldn't start with microservice. You should start with a monolith or modular monolith. So when to start with modular monolith, and there are some reasons on also types. You know, Yagni principle, maybe you will not succeed. Maybe your project will not be succeed. So you may create a simplistic version first as a monolith and see that if it succeed or not. If you want to create a fast MVP product and you want to go market in a short time, then it's also good to start with monolith. Otherwise, making such a microservice system ready for production will be much longer. And if your service boundaries or business requirements are not clear yet, so it's good to start with monolith, because then you can easily refactor a monolith compared to a microservice system. Like moving a functionality from one service to another is much harder to just move functionalities in a monolith system. If you have small team, just don't make microservices, because it will not be easy for you. So if you have a small team, it's good to start monolith first. Okay, you decided to create a monolith system first. However, what can be the development approaches? The first approach can be creating a just monolith, just not thinking about the microservices from the first day. And when you need to convert it to microservice, just throw away all the source code and start from scratch. This can be an approach and can be used to go to market in a short time. Another approach can be creating the monolith and then convert it to a microservice system by keeping the existing code and introducing microservices by the time. Another can be start by separating your system into services, but not too many services, maybe 5 or 6 big services you have in the beginning. Then you break down into finer grained services as your boundaries stabilize, as your business requirements are clear. Or finally, you can create a fully modular monolith, just like each module will be converted to be a microservice in the future. Then it will be much easier to convert to microservice. However, designing a modular system has also some costs, like not hard as creating a microservice system, but it's also hard and it should be well designed. This topic's talk is that actually, how to create a modular monolith first system. Okay, when not start such a modular monolith system or monolith first approach? If you have already replacing a legacy monolith or distributed system, then no need to reinvent the wheel, because you know all the business, you have all the requirements, and you can start microservice first. Okay, how to design a modular monolith system? I will start by introducing why we need to layer our modules or layer our application, so it will be easier later to convert to microservice. Let's start from a single project solution. That means there is no layering. In the solution, you know, there is a single project which contains data access logic, business logic, user interface logic, and hosting logic in a single application. When you want to separate this system, eventually you will need to separate, you will need to completely change actually the hosting logic. You will need to separate your user interface from the business logic and maybe the data access logic. When you convert this to a microservice system, you typically have an API gateway between your user interface and business logic. So you will introduce HTTP APIs, some hosting logic for these HTTP APIs, and also UI hosting logic will be separated. so that they will communicate through REST APIs or GraphQL or whatever you want. However, it will be completely separated. So it's better to start from the first day to separate your business and UI layer. When you separate your business and UI layer, then UI layer depends on the business layer in this .NET project. And for example, in the user interface, in a Razor page model, for example, you can just inject your service and use it. So in this way, they will be separated. However, this may not be enough. I also suggest to introduce a contracts package which contains interfaces of the services. So both business and UI layer will depend on the contracts. Business will implement, UI will use. This is known as the dependency inversion principle. So when you use the customer service, you will now start to use iCustomer service. In this way, there is no dangerous to accidentally access the entities and data access logic and some other stuff that is actually internals of the business logic. There are more actually. We may go step by step, but I don't want to get your more time. ABP offers an module development model. Actually, it can be considered as an application development model that offers some layering. When you implement this layering, it will be easier to host your service or host your module as a service or a part of a module, a monolith application. First, I will introduce this model. Most of the people maybe already knows that because when you just follow the ABP's documentation, you will see this approach. But maybe here you understand better why we decided this model. Okay, in the heart of the everything, there is a domain shared package. This is a .NET project. It typically includes some shared types among all projects, like maybe enums, maybe some constants or something like that. In the domain layer, you implement your domain logic. This model also implements DDD. So we have domain and application separation. So in domain layer, you have entities, you have domain services, maybe repository interfaces, and so on. In the entity framework core package here, it's separated. You have data access logic that implements repositories, basically. We have an application contracts package, which includes your interfaces of your application services, and an application package that implements these interfaces using the domain services and objects. In this model, we have an HTTP package that implements the same application service contracts as REST APIs. In this way, this module will also be able to consume it as a REST API in addition to just local service method calls. We have a web package, so we have clearly separated the user interface. And finally, an HTTP API.client package that uses the application service contracts and performs REST API calls to that module. So having this is good because you can then share this package to your clients and they can easily consume your module. Okay, with this model in mind, if you want to host this module in a monolith application as a just module, you can have a reference to web project if this is an .NET UI, for example. You need to have a reference to the application layer and the database layer. When you add only these three packets, you see all the packets are indirectly referenced except the client package because we don't need, we are hosting this application module as in process. So when you want to host this module in different applications, you don't need to change any source code in that module. This was the goal actually. When you want to, for example, host this module as a microservice, you all need to have to create a hosting application and add reference to HTTP API application and entity framework core package. Then we run application you will see that all the services of this module will be exposed as a REST API. If you want to host only the user interface part in a separate application, as you will eventually do in a microservice system, you all need to reference to the web package and also HTTP API client package. In this way, whenever the web layer use the application service interfaces, actually it performs a REST API call to the service hosting application. You can also place an API gateway between this application. It becomes like physically separated tiers and becomes a first step to a microservice system. If you want to use this module from another application, like a console application, like another microservice in your system, you all need to have a reference to the HTTP API.client package. In this way, you can consume the same REST APIs over the network. For example, you may have a background service application that may periodically perform some operations in background. You all need to reference to domain and framework code package. You see that we have a single code base, no change. But we can use the same module in very different kind of architectures and different kind of applications. Okay, when you want to host all, for example, you created customer module like that in this model, in this modular model, order module, payment module, basket module. All you need to have to create a monolith host application and add reference to these projects. Then when you run the application, you will see all the modules will compose a single monolith application. Okay, the project architecture was that. Then we talk about the database approach. There can be different database design approach. The first approach can be like creating a single database in the first days because, as I said before, we are starting monolith first and we may not know all the rules, all the database structure in the first day. So one option can be creating a single database. Maybe each module has its own database tables, but still can use other database tables, which can be a problem when you migrate to microservice system. Anyway, in the first days, it will be easier to develop, test, deploy, and maintain because we have a single database, physical database. A drawback or a problem of this approach can be if, for example, if your payment module want to use MongoDB and order module want to use a SQL Server, then this may not be possible because all modules should use the same physical database with this approach because we have a single database. And you should care about the data isolation between modules. One approach can be creating separate schemas if your database technology supports it, or programmatically somehow restrict or manage that customer module doesn't read from the order modules tables. So it's your responsibility actually, because we have a single database. For example, if we are using Entity Framework core, we can have separate DB context classes. For the database migrations, we can have a unified DB context and manage the migration in a single path. Another approach may be starting by thinking the separation in the first day, that I mean, you know that it will be eventually converted to microservice. So we may use different databases from the first day, but it will be obviously a little bit harder to develop. Development side is not maybe harder, but testing, deploying, and maintaining, maybe monitoring all these databases, maybe backup all these databases will be much harder compared to a single database. However, if you have a large team, you can manage it. One advantage of this approach is now customer module can use a different database technology and basket module can use another database technology if you need, just like in microservice systems. And also you don't care about the data isolation because if you don't write the database connection string into from like of different module, it's also it's already impossible to read accidentally from other tables. So data isolation will be established in the first step. But my suggestion can be using an hybrid approach. Hybrid is mostly good. So you may have a single database and separate your databases whenever you need to a different database technology. There are some common principles while you are implementing your data access logic and designing your database. The first rule, of course, do not access to other modules database. If you do that, when you separate databases and migrate to microservices, it will be much harder and you will need rewrite, redesign the database, maybe denormalize your database later. It will be much harder. If you are sure that it will be converted to microservices later, follow this rule. And also, as a result of the first item, actually, don't perform join queries across different modules. If you need that, for example, for reporting purposes or just creating some summary user interface page, you may like denormalize or duplicate the data if you need. And then you can asynchronously update the duplicated data with events or with some kind of replication, whatever technology you are using. AVPs provide some automatical distributed events for all the entities. Maybe you can just listen these events and update your local duplicated data. Okay, the hardest part actually, the integrating the modules. Okay, we have separated everything into modules, but somehow they will need to communicate to each other. When you create a new page, you will see that you will need data from multiple modules. Or when a module does its business, it will need to query some data from other module or publish an event that's consumed by the other module, and so on. So how we can implement this integration? There are some common principles. As first, I want to mention. We already said that don't read or don't use other modules database, and also don't do for internal APIs of a module. Like, I mean, for example, a module should not directly use entities, domain services, even application services of another module. They should talk with specifically designed public integration APIs if you need to synchronous communication. Or if you can implement your logic with asynchronous communication, which is the default approach for a distributed system, so you can use the distributed events. For example, when you place an order, you may need to query the customer information first from the customer module. For this purpose, instead of directly using repository services or entities of customer module, create an integration service that is specifically designed for this operation and use that integration service. Such an integration is good, maybe better for read operations like querying customer example here, or repeatable write operations is also good candidate. Updating and deleting, because repeatable operations are easily to repeat, easily to retry when you have an error. In this kind of operations, you can use synchronous communication. However, don't assume database transaction for inter-module operations. That means if you make a write operation in your module and another write operation in the customer module, you can't assume that it will be transactional, because later or maybe in the beginning, your database will be different. Maybe your database technology will change by the time. So you may not establish a transactional database operation among modules. If you need such a reading, consider using caching and also data duplication to perform a local database table join. I will mention about caching and data duplication in the next slides. Okay, for synchronous communication, if you have designed your solution structure like that, you may have an ordering module which has already layered, and also a customer module. And when you need to query customer from the ordering module, all you need to do is to get a reference to the application contracts package of the target module. You can even create a new package only for integration purposes. So you separate integration services from application service. However, I don't want to make it the model more complicated. For now, I assume that integration services are also located in the application and application contracts package. So all you need to have a reference to the application contract package and use the services with interfaces. When you host this application as a monolith, all you need to do to add reference to the application package from the monolith hosting application. If you then want to separate this monolith application to microservices, all you need to do is adding a reference to the HTTP API client package of the customer module. In this way, the internal or local service call become a REST call without any code change. Okay, let's expand some the caching mechanism which can be implemented with the synchronous communication. The most simple one can be like that. For example, you want to query from order module for the customer again. You just can use a distributed cache here, even if the application is not distributed in the beginning, even if it's a monolith application, you should still use distributed cache because your application, your monolith application may have multiple instances running concurrently. So you cannot use in-memory database. So you use distributed cache to query customer. If it's not found in the cache, you just go to the customer module and query from the database or query from the other module. Other module can also maybe use caching internally. However, it's not our topic now. If it's found in the cache, you can directly use the result. However, you shouldn't forget to invalidate the cache when the data change, because the cached data may be outdated if the customer information is changed. It is customer module's responsibility, and it can invalidate the cache without making any service call to the order module because they are using the shared distributed cache. And it's good to use a real distributed cache server if you are hosting this as a clustered environment. Let's see the implementation in the ABP framework. It's very simple. In ABP framework, we have an iDistributed cache interface. You can just inject it and use its get or add method. The first parameter is a key, and the second parameter is a fallback method that performs the real REST service call if the data is not found on the cache. As I mentioned, in the customer side, we should listen. We can listen the local event handler for the entity change event data of customer entity, which is provided automatically by the ABP framework. In the handled method, we can just remove the item from cache. In the next call or in the next request, it will be read from the database and it will work as expected. Caching pattern was a little bit less complex, but data duplication is more complex and maybe a little bit harder to implement. You have an order module again and a customer module. When you need to query customer data while placing an order, with this pattern, it's best to query our local database first. If the customer was already in our local database, that means a copy of the customer table in our local database, actually, we can just use the local data. if it's not found in the local database, then we can query customer from the customer module. We can even use a cache here, just like the previous example. So we can combine this. If it's requested from the customer module, then to not request again every time, we can just update our local data first, then use that data. Next time we will use the local data. But this time we have a local copy and permanent copy of the customer data. So we need to invalidate this data when a customer information changes. To implement that, customer module can perform an event publishing operation, and we can subscribe that event and update our local data. This is pretty common approach to create a local copy of a remote data. Let's see the difference between caching and the data duplication approach. In the caching, you see caching is already faster and lightweight because we are not going to database at all. With data duplication, it's slower because it includes database operations. Caching doesn't need any synchronization between modules or between microservices in the future because customer module can directly invalidate the data without re-communicate to the order module. However, data duplication requires synchronization and event publishing and subscribing to keep the data up to date. Sorry. With caching, we can only individually access to the cached data because we cache with the customer ID, for example. We can only access a single customer at a time. But if we duplicated the data, we can just query from our local customers database table, and even we can perform some join queries with the local data. Caching has limited offline access because if the data was not already cached and the network connection has a problem, we cannot reach to the query. We cannot reach to the customer module for the query. We may not perform our operation and we may fail. So it has limited offline access, while data duplication has better offline access because we have a permanent copy of the data in our local database. So for caching, I suggest to use if only need to query individual data, but use the data duplication if you need to query mass data or you need to perform join operation between the database tables. You can always combine them together for a best performance. However, the implementation will be a little bit complicated. We are doing like developments in the ABP framework to make this even easier. We already done some of this, but we continue to do. For the asynchronous communication, for example, when we need to know some data change or some information change from another system, or if we want to react to a change in another module or service, then we can use asynchronous communication. In this way, customer module, for example, can publish an event to the event bus and order module can consume it. When you migrate to the microservices, then the monolith host will be replaced with two microservice host applications. So in this way, we should definitely use a real distributed event bus. For monolith application, we can use a local event bus, that means in-process event bus actually, for a better performance and also automatic database transaction if possible. We can use ABP's distributed event bus easily. To do that, we just create a class that stores the event data. We call it event transfer object in the ABP framework, a name invented by our team. Whenever we want to publish an event, we can just use a distributed event bus and use it as publish method, just like here. It's very easy. When we want to subscribe to that event, we can just implement distributed event handler interface with the given ETO class, then perform any operation in the handled method. It's also very easy. All the details will be handled by the ABP framework. We will comment. One thing we should consider is database transaction or transaction, and also exception handling behavior when we migrate to microservices. When we have monolith application, and if we have, for example, if we are using a single database, or for example, if two databases are SQL Server and we somehow arranged the distributed transaction approach, then we can execute the handlers in the same database transaction. I mean, same unit of work. With the database operation code and the event handler code is executed in the same database transaction. To do that, we can just execute all the handlers just before committing the database transaction. If any of the handlers is failed, then it automatically rolls back the database transaction. It's easier in a non-distributed system. However, in a distributed system, there are some systems, there are some approaches. One approach can be using the outbox pattern to ensure the transactional event publishing, and also using the inbox pattern to ensure an event is processed only once. The second one may not be obvious in the first. Maybe it's not easy to understand why we need it. Think that RabbitMQ sends event information to you. You executed the event successfully, but cannot return to the RabbitMQ for the acknowledgement message. In that case, event bus will resend the application, resend the message again by thinking that it's not successfully processed. So inbox pattern ensures that the event is processed only once, even if sent multiple times to our application. And we can use some distributed locking techniques and like systems to ensure concurrency in a distributed system. With ABP framework, when we publish an event to an ABP event bus, it first writes your event to an outbox table within the same database transaction with your business code. So the event is saved only if the transaction succeeds. In a background worker, ABP then gets the message from outbox and sends to the message broker. In the receiver side, ABP receives the message and writes to an inbox table by checking if it was received before, and then executes the events within the same transaction that executes the event, like your business logic that implements the event handler. So ABP also implements reconnecting, retrying, like different kind of publish and subscribe scenarios with your message broker. For example, it's different in RabbitMQ and it's different in Kafka. ABP abstracts all these APIs and automatically does all this works. Uses distributed logs whenever necessary and so on. All you need to do is use ABP's abstractions. Okay, we have designed our system or monolith application as modular, so it can then migrate to microservices much easier than not designing this, keeping this in mind. Let's go to the second part and see how to migrate to microservices. The first obvious change is hosting. When you go to microservice system, you now have multiple hosting applications. In a monolith system, you may have a single hosting application. So you typically create a different microservice host application for each module and create an API gateway between your user interface and the microservices, and a hosting application to host your user interface. If your user interface is like for example, a SPA like Angular, it's already separated from the first thing. However, it was like MVC or some kind of Blazor application, Blazor server application, then you also need to separate this UI hosting application. And also authentication will be changed. I will come to this topic later. Sorry. Now, because we are going to a distributed system, we should use distributed caching instead of in-memory caching. Actually, we cannot use in-memory caching even if the system is not distributed, but is hosted as clustered. And also, we should need to switch to a distributed messaging server like RabbitMQ or Kafka. Another thing we should do while migrating microservices, like replacing in-process service calls with REST API calls or some kind of inter-process or inter-machine communication technique. When we use service interfaces and design our application as layered, as I explained before, all we need to change some packets while creating a microservice system, while migrating. When the ordering has a reference to customers' application contracts, all we in a monolith application, we were using the application package, and in a microservice system, instead of the application layer, we will use HTTP API.client package. In this client package, ABP can also automatically generate the proxies for us. It also handles like errors, retry mechanisms, some kind of authentication, serialization, endpoint discovery, and much more automatically. So you don't change any single line of code while migrating to microservices. You can use some kind of retry tool like Poly to ensure that you will retry multiple times if you have temporary network errors. This is another step. You need to enable outbox and inbox if you are using ABP framework and migrating to a microservice system. It's easy. For entity framework core, for example, you just need to implement has event inbox and I has event outbox interfaces for your DB context and configure the ABP distributed event bus options using like a few lines of a code. Then all the outbox and inbox features becomes a part of your application or service. Database migration system will be changed a little bit, not a little bit, actually completely, when you migrate to microservices. Because when you have a monolith application, when you deploy your system, you are deploying all the modules together. But when you have microservices, then a service can be independently redeployed. It may have some database change. So it's better that it handles its own database migrations itself. For a monolith application, as I said, you can just have a unified DB context that, for example, configures all the modules in that DB context. Then you can use this DB context for your entity framework core migration operations. But when you go to microservices, it's best that every service migrates its own database on application startup and seeds its own data. By thinking that if, for example, your customer modules may have 5 copies, for example, running concurrently, if you don't use some concurrency control system, then all the services may try to migrate database in the same time. So you will have maybe database corruption problems or maybe some kind of errors at least. If you have a multi-tenant system, then it will be a little bit complicated, but actually not very hard. When you have a new when you have a new tenant that has a separate database, our approach is publishing an event and handled in all the services to allow all the services to create their own database tables in that tenant's database. Let's see the authentication and authorization chains. When you have a monolith application, and for example, this is an MVC application to keep it a little bit simpler. You typically have a login page. You save an authentication cookie when the user enters their username and password. Then in every request, the cookie is automatically sent to the server and handled in the server to obtain claims from the authentication ticket. Everything works as expected because it's a simple approach. If you have permission or policy database, you can use that for fine-grained authorization. But when you, for example, want to consume customer module from the order module, no need to an additional authorization because it's like an in-process service call. When it comes to microservices, authentication will be changed. The first step can be login again. However, this time it will be probably a different authentication server application. When you have an authentication cookie, then you request with this cookie to the user interface application. Instead of cookie, you can use different kind of like token-based authentication and so on, but it's not important in that point. In the user interface, you check authentication and maybe some kind of authorization and validate this token and perform some HTTP requests to the microservices through the API gateway. API gateway just forwards the request to the corresponding service with all the headers. So in this microservices, you can again validate the token and the customer or the user. And you may want to additional authorization checks. And finally, you may have some inter-service API calls. In that point, you should decide if you want to authorize this call or not. Because, for example, customer service has a method, has a REST API that performs querying functionality, like customer querying functionality. If you don't make any authorization, any service inside your cluster can directly use that endpoint. And even if you didn't prevent somehow, any user from outside of the world, outside of your cluster can also use it. However, you should, if you configure your API gateway to prevent calls to your internal APIs, then you don't need to care about that. So we should we authorize entire microservice API calls? If you want that, you can just forward your HTTP authorization header to the other service. Then the other service can also check this authorization rule. Or maybe this token has no permission for this operation. So you may need to re-authenticate with the client credentials flow. All this flow may be not familiar to you, but it's not important here, very important here. It's just implementation detail. However, in the latest versions of ABP framework, we suggest to use non-authorized integration APIs for this purpose, unless the services are too critical, like, for example, a payment service may be reauthorized or have some additional authorization rules, or some credit card saving service may have different kind of authorization rules. However, for example, querying customer can be just opened with non-authorized to your internal services. But be careful to not accidentally expose this kind of integration APIs to outside of the world. Development environment will be a little bit harder when we migrate to microservices. Actually, it will be very harder to compare it to a monolith application. In the basic, you may want to develop a service that depends on other services, database, API gateways, and much more. So running all the services, databases, gateways, authentication server, and other infrastructure dependencies locally is very hard. and also consumes your system resources. If you want to run all these services locally, you can use AVP Studio, for example. AVP Studio Solution Runner can easily run all the system with a single click. And also Kubernetes integration can use a Kubernetes cluster to run all the system out of your computer, so it doesn't consume your computer resources. You just focus on your own service. You can use Docker or Docker Compose, custom scripts, Aspire, Thai, whatever you want. So you probably need some tools, some scripts, some system to make the development possible. Otherwise, it will be very hard. Like, it's not possible to run hundreds of services in Visual Studio to develop one service. Deployment will be a little bit different. Now you need to, first of all, you need a DevOps team for that, because you are making a serious thing. Your development team or your company will be big enough to implement that. So you probably will use Jenkins or some DevOps tool, some continuous deployment and integration tool. You will use probably a kind of container orchestration tool like Kubernetes to deploy your services, deploy your system. Even maybe for testing and developing the system, this kind of tools will be helpful. Monitoring, tracing a microservice system will be hard, so you need to establish a central logging system and a kind of monitoring system. So all these steps were some the major points of migrating to a microservice system from a carefully thought monolith modular first application. My talk is over. Thank you all for listening.
Thank you so much for being with us and sparing this time to share your knowledges on designing monolith first for microservice architecture. I'm sure everyone found it insightful. So we still have Q&A section open for you guys if you would like to ask your questions. And we will see you on the next session. Have a great rest of the conference, you guys. Bye.